Hello and welcome to our class this term on applied linear models. So this is Stat 331. My name is Sam and I will be your professor for this class. I'd much rather be teaching you in person, but I'll do my best to make this class helpful and engaging for all of you. So when we talk about regression modeling, I'll give you a very quick overview. So the focus of this class, I mentioned, is linear models, but it's helpful to think of, well, what is regression in general. So here's our working definition for it. So we'll say when we talk about regression modeling. Okay, so when we build a regression model, the goal is can be described as follows. So regression modeling, so the goal is to infer the relationship between multiple variables. So let's define the two key quantities here. So first, the relationship Okay, so when we do regression modeling, we often have one variable that's of primary interest. So this might be the quantity that we want to understand, how it's related to the other variables, or we might want to do prediction. Okay, so in either case, the math is the same. We call this variable of primary interest our response variable. Okay, so we have the response. So sometimes it's also called the dependent variable. So I'll give you both of those names. Okay, so this is the quantity that we're interested in modeling, and so we can call it the variable of primary interest. And so we need to assign some notations to these variables. So often, for the response variable, we usually denote it with the letter y. Okay, so I'll put that on the side there. And so regression seeks to find the relationship between this response, and then we can have a bunch of other variables that we can use to build the model for y. These variables may or may not help explain y, and part of the modeling process is to determine which variables can help explain the response, and then infer how each of these variables affect the response. So we want to model the response in relation to a bunch of what we call explanatory variables. So again, there's a number of different terms for explanatory variables. So you may also have heard these can be called or independent variables. Okay, so in an earlier stat course, you may have seen the case where we were just looking at just one variable, so the relationship between x and y. And one of the main goals of this course is to extend that sort of framework to when we have multiple variables. So there could be p of them. Okay, and okay, so explanatory or independent, and they also go by other names depending on what field of application you're in, and also which quantitative field you're in. So you may also hear before or in the future some of these other names for these explanatory variables. So also can be called covariates. That's more of a statistical term, as variables that could be associated with y. Especially when you're doing like predictive analytics, then you might call these predictors, or those in machine learning might call these features. Okay, so these are all synonyms for the same idea. These are variables that could be associated with the response, and we want to discover how they impact y. Okay, so these are variables that potentially affect the response. I guess impact is probably a better word. So let's get that here. So they potentially impact the response, and we're going to assume these to be fixed. So they might be data that we're able to collect, and then based on these variables, we can try to model Y, or if we have new data, we can try to predict Y. Okay, so there's many applications to this. And as I mentioned on the syllabus, regression models are very commonly used. So whether you're in the natural sciences, or you're dealing with finance, or in engineering, trying to predict reliability or any other things, regression models are one of the most commonly used statistical techniques. So throughout the course, I'll be trying to use various examples from different applied disciplines, so then you can see how these models are useful in action. Okay, so again, I need some notation. So we're saying that there can be many variables, so we're going to make a list of them. So in general, let's say there are p variables, so I'm going to denote them x1, x2, up to xp. Okay, so all right, so I've been teaching at University of Waterloo for 2 years now. So this is my third year teaching here. And so before I came here, I worked at the University of Florida down in the States, and I hope to tell you some stories about those experiences over the course of this term. But for now, I'll just mention one thing, and that's you think of common animals on campus, right? So at the University of Waterloo, I mean, we all know the answer to that, or you should all know, is geese. Okay, so very commonly you will see Mr. Goose walking around campus, often with Mrs. Goose. So what would be the equivalent at the University of Florida? And you can sort of get a hint from looking at the school's mascot of UF, and that would be they're called the team is the Florida Gators. Okay, and so not surprisingly, that's named after the alligator, or the American, specifically the American alligator. Okay, so I have over here kind of a stylized picture of an alligator, so that you get a sense of what these animals look like. I mean, this one looks pretty friendly, but in general, if you're around alligators, you better be careful, because they can be quite aggressive. And so we would have a pond on our campus, and if we wanted to go alligator watching, we just go walk down to the pond, and on a good day, you might see some of our friends popping up their heads from the surface of the pond, and we could try to count how many alligators there were. And so, as a very common Floridian animal, they have been subject to studies, and so in particular, they can grow to be quite large. Okay, so just keeping this framework in mind, I'm going to list some variables here, okay, so that we could potentially collect about these friends. And so let's start with one obvious measurement. So we can measure, so alligator data. Okay, so as kind of a way to measure their size, we could put length in meters. So according to the data set I was looking at, they could range from about 1.2 meters when they're young, and they could grow as large as almost 4 meters. Okay, so they can be very massive, and sometimes they can be found outside their habitat. For example, in golf courses, or in people's the swimming pools of people's backyards. That's very common in Florida, and sometimes, yeah. And then there's this company called the Gator Boys. So if you have a nuisance alligator walking around your backyard, then you can call these guys, and they will come and move it to back to its more natural habitat. And so. About a couple decades ago, some people did a study on alligator length, and so they captured about 200, a little over 200 alligators, and they measured their length, and then they also wanted to find out how the length might be associated with various characteristics. So, for example, male and female alligators tend to be of different size, so you could collect that in the data set. So male or female. And then the rest of their variables in this case was associated with, well, what kind of, what comes to mind? Like, what's associated with an alligator's size? Well, I mean, you could consider, well, what they like to eat. Okay, and so what they eat could be very much associated with how big they grow to. So what they did on these poor 200 alligators, where they cut them open and they looked at what was in their stomachs. Okay, so then there's this big belly there. They opened it up to see what they had eaten. So what was their most recent meal? Okay, so then you have a bunch of so let's call this the mass in the stomach of various food items. Okay, so these are the categories of food that they classified into. And if I was teaching live, I would ask for your participation at this point, but in this case, I would just have to tell you. So, the most common food item found in their stomach was fish. So, various kinds of fish that they had found while lounging in the lake or their swamps. Another food item was invertebrates. Okay, so so this is a kind of a broad class of these often smaller things like snails, insects. Okay, so alligators eat those as well. The third category is reptiles. Okay, so what do reptiles include? So if the alligator ate a turtle, that would be considered a reptile, and also researchers sometimes also found alligators in alligator stomachs. Okay, so I don't know how that happened, but they did find some alligators. Another class is birds. So various species of birds. Maybe if they were lounging on the surface of the lake, they might have gotten eaten, unfortunately. So the researchers found some remains of birds in their stomachs. And then the last category, as we often need, is everything else. Okay, so other. So what were some things that were in other? Okay, so sometimes they chewed on some plants, so they found some remains of plants. Sometimes they accidentally swallowed some rocks and sometimes garbage from humans, and they also found remains of pets. So that's very. So that's why if you ever visit or people who have pets in Florida, you're quite careful. Don't go too close to lakes and swamps, because an alligator would come out and eat your dog, and you don't want that to happen. So pets were also found in their stomachs. Okay, so just to remember this framework. Okay, so that we have a response variable and various explanatory variables. So as I kind of alluded to, what we're most interested in predicting or modeling in this list of variables is the length. Okay, so the size of the alligator. So I'm going to label this as our response variable. So I'll call this y. Then you have a bunch of predictors. Okay, so all these other variables could be used to help explain the length or why the alligator has grown to that particular size. And so we can call these our x's. So we have so as you notice, the predictors can sometimes be categorical. So in this case, male and female. So we could label one of these 1 and the other 0, as we'll later learn. So this is an example of a categorical variable. And then here We have 5 other variables, which is like how much of each food item they found in their stomach. So these we can consider to be continuous variables. So suffice for now, let's just label them. So we can call this one x1, the first predictor, and then we have all these measurements of masses of food in their stomachs. So we can label them x2 up to x6. So in total, we have, in this case, 6 explanatory variables for our main variable of interest. Okay, so I just want to give that as give you a kind of a more concrete illustration for the idea of having a response and multiple predictors. Okay, so next then is to think of the relationship between them. So in our early math courses, we learned about functions. Okay, so we might imagine that there's a function that relates y with these x's. Okay, so we might imagine there's a function that can explain the relationship. We can explain y in terms of the x's via a function. In terms of, okay, so I'm going to go back to general notation here. There's 6, but in general you're going to say with p explanatory variables of the x's using some function so that y is, okay, so use f as our generic notation for our function. So think of the response y as a function of the x's. Okay, so in this case, you put in a vector into this function, right? It's all these x's, and then the output of the function is some value y. Okay, so in the most general sense, regression. So we can frame any problem like this as a regression problem by fitting a function f. Okay, so that's regression in general. Now in this course, we will primarily focus on linear functions for f. Okay, so hence we call these applied linear models. So I'm going to give you the form of that. So basically, when we say linear, it means that we model the response y as a linear combination of the x's. Okay, so I'll give you a functional form for that, so you can see what that looks like. So remember that these x's, you could build other predictors. For example, if y was more associated with the square of x, you could transform these predictors. So when we say linear, we mean linear in terms of the parameters, as I will define next. Okay, so this is a very broad class of models, and we're going to focus on the linear regression model. If you think of, well, what's the simplest type of functions you can think of? Well, you would probably think of, well, lines, right? And so linear is one of the simplest classes of models, but yet very useful because often these kinds of relations are really complicated and can be approximated quite well using the simplest class of functions, which is linear regression models. But yet so simple, but yet very useful in many applied domains. Okay, so the linear regression model assumes that. Okay, so here's the general one. So here's a specific case where when we look at linear regression models, so we model y in terms of a linear combination of the x's. So we can write it in this form. Okay, so we're going to introduce some parameters. So we generally use betas for the parameters. Okay, so I'll write it down first. So we'll have a beta 0 and then beta 1 times x1 and the beta 2 times x2 and so on, and then beta p times xp. And at the end, okay, so we'll explain this more fully as we go on. But for now, we'll put an epsilon, okay, at the end. So let me give you a rundown of what all these things are. Okay, so let's make a list. So we give y. Okay, so that represents the value of the response. Okay, and then we have x1 up to x p. So these are the values of the p explanatory variables. And we're going to assume these to be, from a statistical point of view, we're going to assume these to be known constants or fixed. So we're not going to put probability. In other words, we're not going to put probability distributions on the x's. We're going to assume that we can either know them or can measure them. Okay, so we're going to assume to be fixed constants. Okay, so what else have we got? We have these things, these parameters that are, well, that's what we call these. So let me just write that down next. So it's beta 0, beta 1, and up to beta p. Okay, so these are what we call the model parameters. Okay, so generally what we have to do is, from our data, we're going to one of the key things we'll be doing in this class is estimating the values of these parameters. So how do we best fit this model? Okay, so that'll be a big question that we'll be answering in the coming classes. Okay, so why do I have this? So we can kind of break this up as you've seen in one of your earlier stat classes. You probably saw the case where there was y and then there was x. Okay, so the interpretation of beta 0 is the same. We call this the intercept. So you can see that this intercept term represents the value we would model for y if all the x's were 0. Okay, so that's the interpretation. I'll write this down. So the expected value of y when all the x's are 0. All xj is 0. Okay, and then the non-intercept parameter. So you notice beta 0 is on its own, and then beta 1 and beta p is where we get the linear combination of the x's from. So each of these betas is multiplied on the corresponding value of x. Okay, so how can we think of these? We can say that these parameters, so these quantify the effect of xj on y. Okay, so I'm just using xj as a shorthand, so j goes from 1 to the p predictors. Okay, so we have y, we have the x's, and then we have the parameters for the model that we will fit, and we will learn how to fit. And then finally, we have this epsilon term. Okay, so this we simply call this our random error. Okay, so you may ask, well, why do we need an epsilon term? And so, well, from a practical point of view, let's explain it from that point of view first. Clearly, there may not exist a linear combination of the x's that perfectly models the y, and this allows for the fact that the model will not perfectly fit the data. As probably one of the most famous sayings in statistics is that all models are wrong, but some are useful. Okay, and so that's what we hope to do as we fit these linear regression models. We know that they're not going to perfectly explain the data, but hopefully that gives us a useful sense of the relationship between the x's and y, so that we can understand the relationship better, and then perhaps even make predictions for the value of y when we plug in some new data where we want to do some forecasting, for instance. Okay, so that's the role of the random error, and so this is also where probability distribution comes into play. So far I've just written all this stuff. Remember x's we're treating as known constants, and then betas are just values we estimate. So everything in here is just a bunch of constants. X's are known and betas will be estimated. So the only thing that controls the stochasticity or having a probability distribution comes from this random noise term epsilon. Okay, so that's where we're going to assume a probability distribution, and the classic assumption is simply that the errors are normally distributed. Okay, so we're going to assume it has a normal distribution. Okay, so we're like this. So epsilon. So this tilde denotes that you can read it as epsilon is distributed as. Okay, and then we put something here. And so the shorthand for normal, I'll use cap n. And normal distribution has two parameters: the mean and the variance. Okay, we assume that the mean is 0. So in other words, on average, the value of y is explained by this linear combination of the x's, but there can be some variability around it when the model doesn't explain it perfectly. Okay, so that's captured by the sigma squared parameter, which is the variance parameter of this normal distribution. Okay, so this is the mean, and this is the variance. Okay, and so as mentioned, we make this assumption as in general the model will not perfectly explain the data. Okay. It will not perfectly explain why. Okay, so that's the basic linear regression model that we will be spending much of our time on this term together. And so just to end off today, let's see what this assumption means in terms of. So let's ask the question then: what is the distribution of y under these assumptions? Okay, so I'm going to give myself a little more room here. So remember that the x's are treated as fixed constants, and then so are the model parameters. They just have to be estimated. So the only randomness is coming from this epsilon. Okay, so what does that mean for y? Okay, so to answer that question, I'll give you the answer today, and we may have to go back and remind ourselves of the properties of the normal distribution. Okay, so what we're doing is we're taking this constant and adding the epsilon term. So this part is a random variable, and so because epsilon is a random variable, so therefore y is also a random variable as a function of this fixed part plus epsilon. Okay, so let's answer the question. So the probability distribution of y. Okay, so let's do it in 2 steps. So let's ask, well, what is the expectation of y? So this is where we need the expectation and variance operator from working with probability distributions. So that's E of y. So that's what is the average value of y in terms of its probability distribution. Okay, so that means you got to take the expectation of everything on the right. Okay, and so what's the expectation of a bunch of constants? Well, it's just the constants themselves. Okay, and And so let's remind ourselves that expectation is a linear operator, so we can take the expectation of each of these terms and add them all together. So the expectation of beta 0 is just beta 0, and same for each of these terms as they are just constants. So the only thing that is random, as I noted here, is epsilon, and what's by assumption the expected value of epsilon? Well, you look down here, epsilon is assumed to have a normal distribution of mean 0, so the expectation of epsilon is 0. So that means the expectation of y is simply this linear combination part, which involves the x's and the betas. Okay, so that's the expectation of y. Okay, so therefore, now you remember I wrote here the expected value of y when all the x's are 0. So therefore, you can see that's explained here. So when all the x's are 0, then the expected value of y is beta 0, which is the intercept. Okay, so that's the mean of y, and then we also need the variance of y. Okay, so again, you take the variance of y, you take the variance of everything over here. Okay, so what happens when you take variance of a constant plus some random variable? Well, the constant just drops out of the variance calculation. Remember, the constant just shifts the random variable. Okay, so the variance of y, none of this matters for calculating the variance, so it's simply the variance of epsilon. Okay, then we dropped all the constants, and so again, by assumption, the variance of epsilon is sigma squared, so we have our answer. Okay, so we have the mean and variance of y, but what family of distributions does y belong to? Okay, so that's the last part to finish this point. And here we need to remember that linear combinations related to normals are still normal distributions. Okay, so y is a function of this normal plus a bunch of constants. Okay, so therefore the answer is y is normally distributed with this mean and variance. Okay, so we'll use this practice using this tilde notation. So distribution of y is normal, and then we write the mean is this linear part. The variance is sigma squared. Okay, so under our assumptions, this is the model that we'll be working with for much of this term. Okay, so that's in terms of the material. That's what I wanted to introduce to you today. So make sure you read carefully the syllabus, which is also posted alongside of this video. That contains the key information on how you will be assessed. So there will be a combination of assignments, quizzes, and then there will be a project at the end of the term. So make sure you read everything there. It has all the important information, so do read the syllabus carefully. And finally, we will have a Piazza forum, so that you can ask questions, and you can post your questions if you would like to discuss any of the course material. And finally, I will also set up some online office hours as well. So these will all be announced on Learn in due course. So with that, again, I'd like to welcome you to this course and look forward to teaching you the best I can, so that we can have a good term together.